Okay, so for problem 1, you could have used formula number 2 or number 3. I prefer formula number 3, so I'm going to show you how I would use it using that one. So our formula says our final velocity equals our initial velocity plus our acceleration times time. So if I come back over here to my list of variables, I can plug in my values that I was given for the problem. Make sure you get that negative on the 10. And then t I would leave, or time I would leave as t because that is my unknown. So then I would need to solve this out. So I would need to subtract the 25 from each side. So I would have negative 25 meters per second, I should put my labels in there, is equal to negative 10, that is meters per second squared, times time. Now I'm going to divide by the negative 10 on both sides. And now over here, when I do that division, they will cancel each other out except for my seconds. So when I divide that out, I get 2.5 seconds is equal to my time. Now be careful here, because we were applying this only to the first half of the motion. So this time of 2.5 seconds is only the amount of time it takes to go up. So my total time would be double that, because it takes 2.5 seconds to go up and 2.5 seconds to come back down. So my total time is equal to 5 seconds. Okay, the next question, problem number 2. I would end up using formula number 6. Notice there was only 2 formulas in that entire list that had distance in there. So when you have distance either in the problem or as your unknown, you probably want to look to those 2 formulas first. So formula 6 says I take d equals 1/2 acceleration times my time squared. D is my unknown, so I'm going to leave that as d. My acceleration tells me it's 3 meters per second squared. And my time was 12 seconds, so we need to square that. So follow my order of operations. I would have d equals 1/2 times 3 meters per second squared times 144 seconds squared. And then I can go ahead and multiply that all out. Notice my seconds squared and my seconds squared are going to cancel out, which is just going to leave me with an answer of meters. So if I take 1/2 times 3 times 144, I end up getting a distance of 216 meters. Okay, and then problem number 3. Let's see, I was going to end up using formula 2 or 3. I'm going to go with formula 3 again. And I know that my final velocity is 0. My initial velocity, that's my unknown, so I'm going to leave that as v sub 0. Plus my acceleration is negative 10 meters per second squared. And my time, okay, I was only working with half of the motion, so my time that I was working with is 10 seconds. Start to solve that out. Okay, and then if I move the 100 over by adding 100, I get 100 meters per second is equal to my initial velocity. Now, I don't have to double this or anything like I did on that previous problem with the time, because I already took into account the half of the motion, and I already took care of that over here when I went from 20 seconds to 10 seconds. So my initial velocity would have to be 100 meters per second. Okay, now problem 4. I would use formula 6 again. So this time I know my distance is 180 meters. My acceleration is 10 meters per second, and I'm looking for my time. So when I multiply this one out, I get 180 meters. 1/2 times 10 meters per second is 5 meters per second, and I still have t squared. Divide both sides by 5 meters per second. And 180, let's see, divided by 5, that ends up giving me 36. Oops, 10 meters per second squared. Put my square on there. And my units over here, my meters would have canceled out when I invert and multiply. So I would be left with seconds squared is equal to time squared. Now, in order to get rid of a square, we have to square root both sides. So when I square root each side, the square root of 36 is 6, the square root of seconds squared is seconds, and then the square root of t squared is just t. Okay, so I end up with t is equal to 6 seconds. Now on this one, I do not need to double it because this one, it was just dropped off of a cliff. So it wasn't motion going up and motion going down. So I would end up with 6 seconds. Now the last thing you would want to do is you would want to go back and make sure we check all these for significant figures. Okay, so for this one right here, the initial velocity, that would be an infinite number of significant figures because it's dropped, so it's 0. My acceleration due to gravity is 1 significant figure though, and I was using multiplication, so it looks like I have that one is okay for sig figs. If we go back to problem 3, let's see, this one is an addition problem, but there's multiplication involved too. Let's see, I would have 1 significant figure here, and I would have infinite there, so I believe I have that one okay for sig figs too, because 100 has just 1 significant figure. Okay, problem 2, I bet we're gonna have to round this one. So my original problem, I have 1 significant figure. This is all multiplication, so my final answer can only have 1 significant figure. So I would want to come back here and change my distance to just 1 significant figure, which would end up being 200 meters. Okay, and then problem number 1, let's check this one out. There was multiplication and addition, so we've got to pay attention to that. I'm only allowed 1 significant figure, and it looks like that one turned out okay too. Okay, so those were just a few examples of how you might be expected to use some of these formulas and to manipulate them. Again, these are not the only formulas for linear motion in physics, but they are the basic ones.